Okay, so we're going to revisit the question from the last video. So we're still looking at horizontal projectiles. And this time, we're actually going to think about solving this using graphs instead of kinematics, okay? So we have an object launched horizontally from a 50-meter cliff. So a 50-meter cliff, okay? And it's launched with a velocity of 30 meters per second, okay? And as we're getting started here, a couple of things that are going to help us out here. First, it's helpful if we say that our starting position is 0 meters. Okay, so we're going to say we're starting from 0 meters. And these are all things that are going to help us because we're going to use graphs to answer this, so it's going to help us draw our graphs. Okay, and also, Generally, I'm going to say pick up or down to be positive. Doesn't matter. Just do what makes sense to you. Whenever we're working with graphs, I'm going to say up is positive just so that we can avoid confusion. Okay, because I think if we jump back and forth there, it's going to get kind of confusing. Okay, so because this is a projectile, because it's in free fall, we know some things. For x, we know it's in constant velocity, so that v is equal to x over t. We know that v is equal to 30. We don't know what delta x is, okay? And then in the y direction, we know that v naught for y is equal to 0, and that's because it is a horizontal projectile. We know that acceleration is going to be equal to negative 9.8 meters per second squared. And then finally, we know that it's going to have a vertical displacement. Sorry, let's use delta y there. Of 50 meters, and so since it's going to end up 50 meters below where it started, and since up is positive, that's going to be a displacement of negative 50. We don't know the final velocity for y though, okay? And then we also don't know the time, okay? So we have three things that we can find here, okay? And so I'm going to start actually by drawing graphs, and I'll make some comments on those graphs as I draw them. So let's start by looking at the horizontal stuff. So I'm going to actually divide the screen in half, or I guess this wouldn't be a half. I guess this would be like a quarter maybe, but we're going to divide it and put the horizontal stuff here and the vertical stuff here, so we can be careful to keep it separated so we don't get confused. Okay, so we'll start by drawing a velocity graph for x. Okay, we have a constant velocity here of 30 meters per second. Okay, and we know that this area here is going to be delta x. Okay, we don't know delta x, but we do know the area there is delta x. Okay, and so we can even write, well, okay, 30 meters per second would be equal to delta x times t. If we want to draw a position graph for x, it's just going to look like this. Because it's traveling horizontally at a constant velocity. We know that the slope here is 30 meters per second. Okay. All right. So the that was the horizontal velocity. By the way, that notification up there, that was in reference to University of Texas, I believe, won this weekend. So anyway. Alright, so moving over to the vertical direction, we know we're going to draw a graph for the y velocity. Okay, so Vy. Okay, we don't know what t is, but we know that we start from 0, and we're going to go like this. Okay, it's going to get more and more negative. Okay, we know that the slope here is negative 9.8 meters per second squared, and we also know that the area is equal to delta y. Okay, and we know that delta y is going to be equal to negative 50 meters. Okay, so we'll say negative 50 meters going to be equal to the area here, it's 1/2, times the base, which would be t, times the height, which would be v final. Okay, and then we can also draw right here an acceleration graph, a versus t, where a is equal to negative 9.8 meters per second squared. Okay, and we know the area here is going to be equal to delta v. Okay, and so if we, let's go ahead and write that out. So negative 9.8 times t equal to delta v. And remember, delta v is just v minus v initial. V initial here equal to 0. So that means that v is equal to negative 9.8 times t. Okay, so if I'm trying to solve for how much time, I can take this velocity here and put it in for v there. And so, okay, negative 50 meters equal to 1/2 times t times negative 9.8 times t again. Okay? Or we'll get rid of the negatives and multiply the 2 over. So 100 equals 9.8 t squared. Okay? So to finish solving this, we're going to divide by 9.8. And then we'll take the square root, and we'll get that t is about 3.2 seconds. Okay? So t equal to 3.2 seconds. I can come back to here and say, okay, well 9.8 times 3.2. Alright, and that's going to give me my final velocity for y of 31 meters per second. And it's negative 31. Okay? And I can also take my 3.2 seconds over to here, okay, and say 30 meters per second equals delta x times 3.2 seconds. Okay, so I'll divide that over, and I get that, wait a minute, something not right here. This is backwards. So delta x equals 30 meters per second times t, and we'll put into that. Okay? And so delta x would be 30 meters per second times 3.2 seconds, and that's going to give us horizontal displacement of 96 meters. Okay? So that means it's going to fly 96 meters horizontally before it hits the ground. Okay? Now, some questions are going to be easier or make simpler, I guess, to figure out using the graphs. I think this particular question is a little trickier using the graph, maybe. But there is some insight to be gained. And really, these graphs will become a little bit more useful when we're looking at projectiles that have been launched at an angle. Okay?